Section 6.1, Confidence Intervals for the Mean, with sigma known. The point estimate is the signal value estimate we have for the population parameter. In other words, if we want to determine what the population average is, we use a point estimate, and the best way to do that, and I put it here, the most unbiased point estimate, is the sample mean of X. For example, researchers collecting data about college athletic conferences and student athletes. A random sample of 40 athletes are selected. Their number of hours spent on recorded athletic activities for 1 week is recorded. Find the point estimate of the population mean, mu, the mean number of hours spent on athletes' athletic activities by all students, athletes in the conference. So this is basically a list of 40 different athletes and how many hours a week they spend on athletic activities, whether it be actually practicing or lifting weights or going to training, what have you. And my point estimate is basically I add up all these hours, I divide it by 40, it's 842 hours total divided by 40, and I get 21.1 hours on average among this group of 40 athletes. Here's another group, a different group, 30 student athletes, how many hours they spend on athletic activities. And when I add all these rows up and then divide it by 30, I get 626 divided by 30, 20.87. We'll be coming back to these in a moment. Now, keep in mind, it's very unlikely that the sample estimate of those 40 athletes and the 30 athletes is exactly the same as the population mean. But we know it will fall within an interval, most likely, within a range. I've got a number here. Suppose I got a point estimate of a sample mean 21.1 as a representation of where it is to the population. Suppose I found a margin of error of 0.6. I'm just throwing some numbers out here. And I would say that margin of error allows the population estimate to be between 21.1 minus 0.6, which is 20.5, and 21.1 plus 0.6, which is 21.5. I'm sorry, 21.7. So when we look at that, we know the population mean falls between 20.5 and 21.7. Now, we're talking about normal distribution here. We look at a bell curve, and we know what percentage of the area is under the curve. We can use our z-score. But when we're looking at an estimate, we have to go down the middle and then look at equidistance from down the middle on each side. So if I want a confidence interval, C, of 90%, and that's the blue in this curve right here. That means at that minus z to the plus z, the blue part, is 90% of the whole curve. That's a remaining 10%, and 5% would fall within, from the very beginning of the curve on the left to that minus z, and another 5% would fall from the z to the other right side of the curve. 5% outside that, plus the 90% for the confidence level, plus another 5%, 100% or 1. And I could determine the z-score for 90%. And if I do the z-score, if I don't find a z-score at 90%, I gotta look at this. And it's easier if I go to the positive one first. Remember, that is 90% each side. 90% total, or 45% of each side. So from here to here is 50%. And then, if I want to know what this z-score is right here, that would be from here, in the middle here, to there. And we already said that's this is 5% each side. So 100% minus 5% would be 45%, or 0.45. Because this is 0.5 here, and this is 0.5 here. That's 10%. So 0.5 plus 0.45 equals 0.95. And I gotta find, and remember, all these numbers here are percentage under the curve. If I go here, the closest it comes is between 0.9495 and 0.9505. Right between that is 0.9500. So 1.6, and that's between 4 and 5. So it'll be 1.645, which is how I got this number right here. So that z right here is 1.645. And then since it's equidistant, the negative z would be negative 1.645. Equidistant from the center. And if you're not sure, let's look at what he, remember, this is 0.05 here, and then this is 0.5 here. And we always start the curve measurement from the very left up to that point. So we look at what 0.05 is. 0.05. Let's see if we can find 0.05 in the curve here. And it would be right between here, 0.0505 and 0.0495, which is negative 1.645. And that's where we get that. Sampling error is the difference between the point estimate and the actual average of the population. Most of the time, our population mean, the mu, is unknown, and the sample average, which is x to the bar over it, varies from sample to sample. But we can calculate the maximum value of the error to know the level of confidence. This is called the margin of error. How much is the error from the population? What range does it fall within? And that big E is basically found by the Z we're looking at times the standard deviation of the sample mean. Or another way to find it is Z score times the sigma divided by the squared number of samples within that group. You gotta make two assumptions here. The sample size is greater than or equal to 30, and the population is normally distributed. It's a bell curve. So let's look at our data from before, the 40 athletes and the number of hours they spend on athletic activities. We already found our sample mean of 21.1. And I want to find the margin of error with a confidence interval of 95%, which means I'm 95% confident, or if I have 95 different groups out of 100, what range they'd fall in. And I'm given standard deviation 2.3. To find the margin of error, E equals the z-score for that 95% times the standard deviation, which is also found by the z-score, times the standard deviation divided by number of samples, square root. And I got 1.96, and I'll show you how I found 1.96 in the next page. 1.96 times 2.3 divided by square root of 40 samples. That ends up being 0.713. So I'm 95% confident that this sample has an error range of 0.713 hours, plus or minus, based on that 21.1 hours. So let's see how I arrived at that 1.96. My curve here is 95%. I'm looking at 95% confidence interval. Or if I took 100 different 100 different groups, 95 of them would fall within this range. So let's remember, but it's 95% down the middle, which is half of 97 is 0.475 on each side. 0.475 here, 0.475 on this side, under the curve, the blue part. I want to know what score this is right here. Well, from the very beginning to halfway is 0.5. And then 0.5 plus 0.475 from here to this point is 0.5 plus 0.475, which is 0.975. 0.975. And if I look at 0.975, 97.5% space under the curve, I find it right here. Here's 0.9750, which is 1.96, which is what I got before. So that's where I got the 1.96. And then it's equidistant on the other side, so it's negative 1.96. But let's make sure. That's from the very beginning to this point is 0.025. So we would look at find where 0.025 is, and that would be right here. And that is negative 1.96. So that's where we got 1.96 for our calculation. Remember, we're going down from the mean, right in the middle, and then equidistant from each side. Now let's look at our group of 30 student athletes and their hours. We had a total of 626 hours divided by 30, which is 20.87. And it's greater than or equal to 30, and the samples are random, so we can do this normal calculation. And our equation is there's margin of error is the z-score times my sample deviation divided by number of samples. And we know what our z-score is at 95% confidence, 1.96. We did that previously. 1.96 times 2.3 divided by square root of number 30, which is number of samples, get 0.823. So with this group of 30, instead of the 40 from the previous one, we now have a sample mean that has a 95% confidence interval with the error of 0.823 hours. And as I did before, all I'm going to do, here's my normal distribution, and I found out it's 1.96, negative 1.96, same confidence interval, but it's 0.823, 20.87 plus 0.823 equals 21.693, and then 20.87 minus 0.823 equals 20.047. So a 95% confidence interval says we're 95% confident this sample is a representation of the population when it's between 20.047 and 21.693. Now we can also determine the confidence interval, which is what we've done for a population. It's very similar. Sample mean minus the error, which is between our population mean and sample mean plus the error. And we've already done this actually. Again, it samples have to be 30 or greater, it's random, and we also know our standard deviation, that small sigma, looks like a small cursive O. Sample statistics is basically found by, we've already done this, the sum of all the sample sizes divided by number of samples. We find the critical value, as before, the z-score, which is finding the percentage under the curve. And our last point is what we've already done. Our sample mean minus our error we found, and our sample mean plus our error we found. And that U is saying it's between those two areas for the population mean. I'm going to show you a little table here. We developed these for 90% and 95%. You recognize these numbers are 95%. The confidence interval 0.975. The z-score 1.96, 1.645. I found 85%. We can go back to the table to look. It's 1.44. And a z-score 75%, 1.15. The population deviation hasn't changed. Square root of 40 is still 6.3245. My calculation error is 0.418. And what you notice, what we got going on here is the lower the confidence interval, the closer it's going to be to the population mean. In other words, the higher the confidence interval, the wider the range is going to be. We have to be more careful. The less careful we have to be, we get closer to what it actually is. So, more confidence you want, the wider your range is going to be for your lower and upper limits. Another example of this. College admissions director wishes to estimate the mean age of all students currently enrolled in a random sample of 20 students. The mean age is found to be 22.9 years, which seems kind of old for the mean age in college, but that's regardless. Past studies, the standard deviation is found to be 1.5 years, and population is normally distributed. Let's do a 90% confidence interval. Well, when I find the margin of error, which is E, defined by my z-score times my sample deviation divided by number of samples, it's 90%, which is 45% each side. And we already found that before. And a z-score 90%, which is 45% each side, is a 1.645. And 1.645 times a sample deviation of 1.5 times the square root of 20, which is the number of samples, 0.55. So that's my error. So my left endpoint would be 22.9 minus 0.55, which is 22.35, as I'm showing you right here. This is simply 22.5 minus 0.55. And then on this side, it's 22.5 plus 0.55. So our population mean is going to fall between my sample mean minus my error I found and my sample mean plus the error I found, which means it falls between 22.35 and 23.45. The mu is population mean. We don't know what it is, but it's between those two numbers. Now, we're often asked when we're doing an analysis based on samples and compared to population, how many samples do you need to collect based on getting a good answer? Well, it really depends on what your confidence level is. We can rearrange the margin of error formula to get the number of samples by having n equals the z-score, which we get from the confidence interval, times sigma, which is the standard deviation, divided by the error, all of that squared. In our original example with the 40 athletes, the number of hours spent on athletic activities a week, if we wanted to get a 95% confidence interval with plus or minus 0.5 hours of the population, how many do we need? Well, the confidence interval we say is 0.95 or 95%. We've got, that ends up being 1.96 for a z-score, which we found several times. They give us a deviation of 2.3. So plug in this formula, 1.96 times 2.3 divided by 0.5, all of that squared is the 1.29 or 82. So I need 82 samples. What if it's 75%? 75% has a z-score, and we found out a couple of pages ago, of 1.15. Same deviation, and it says instead of 0.5, it's 0.75 hours. So it's a wider range. So 0.15 times 2.3 divided by 0.75. All that squared is 12.43 or 13. So if we want a lower confidence interval and have a wider range for what is acceptable within the error, be much smaller, 13 compared to the 82.